we're talking about linear dependence. Not done here. Anyways, let's move on. Please pay attention. I want to take more examples on what we've been dealing with. Having to do with elementary row operations and getting the relationship between vectors, the elements of the vector space. So we want to take more examples that we have in the lecture material, so that the span shows that the span 1, 0, 1, minus 1, 2, 3, 0, 1, minus 1 is all of R, so that the span blah 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 1, 0, 1, minus 1, 2, 3, 0, 1, minus 1 is all of R3. In the last class, we defined what a span is. We said listen now. Span would mean if you have a span of this subset, it means that all possible vectors, the set that contains all possible vectors will form as linear combinations of the elements A. That means that the span of this is going to contain elements which will be given by, say, alpha 1 multiplied by this plus alpha 2 multiplied by this plus alpha 3 multiplied by this, where alpha 1, alpha 2, and alpha 3 are some real numbers. Do you understand this? Okay, so we want to show that the span of this set of vectors is all of R3. What does that mean? That means we want to show that, please pay attention, we want to show that every R3, the R3 simply means three-dimensional vector, so to speak, a three-dimensional vector of real numbers. So if this is all of R3, it means that we will be able to write any vector A, B, C in terms of this, or as a linear combination of these vectors. That is what we mean by that. So that means that, listen now, I know R3 is simply A, B, C. This is what we mean by R3. So these are elements of this vector space R3. So if the span, pay attention, if the span of this set is all of R3, then I should be able to write any element A, B, C, okay, any vector A, B, C in this form, as a linear combination of the elements right here. So that is the meaning of that statement. So that means I should be able to write A, B, C in terms of these vectors such that I will have alpha 1, alpha 2, alpha 3, okay, to be, to be available or to exist for any combination of A, B, C that I have. So that is that about that. So we say that let A, B, C be the elements of that vector space R3, and if this is the span of R3, if say let S represent this set, S equal to 1, 0, 1, minus 1, 2, and 0, 1, minus 1. So it follows that if this, pay attention, if span S is equal to R3, you know what I mean by that? Span S is all, if span S is all of R3, then A, B, C should be writable in the form alpha 1 into 1, 0, 1 plus alpha 2 into minus 1, 2, 3 plus alpha 3 into 0, 1, minus 1. You get that? Where alpha 1, alpha 2, alpha 3 are some real numbers. You get that? and this should be writable for all, okay, for all A, B, C, A are real numbers. This should be expressible for any combination of real numbers A, B, C. So this is what we want to establish now. So that means that if we have this, we have now an equation. Please pay attention. That means I should be able to write, I should be able to say that A, B, C equals to, what is that going to give us? Multiply alpha 1 into 0, alpha 1 plus minus alpha 2 into 2, alpha 2, 3, alpha 2 plus 0 into alpha 3 into minus alpha 2. Okay? Do what I'm doing, right? So this is going to give us, this should give us alpha 1 minus alpha 2, comma 2 alpha 2 plus alpha 3, comma alpha 1 plus 3 alpha 2 minus alpha 3. That means that A should be equal to this, B should be equal to this, and C should be equal to this. Is that clear? Alright, so this means that I should have alpha 1 minus alpha 2 plus 0 alpha 3 equal to A. I should have 0 alpha 1 plus 2 alpha 2 plus alpha 3 equal to this. I should have alpha 1 plus 3 alpha 2 minus alpha 3 is equal to C. And if I write this in matrix form, I should have, in matrix form, I should have this to be, so this will not be, the column here will just be those formed by this. 1, 0, 1. Always check that at the end of the day, this should be what you end up with. Minus 1 will be 0, 1, minus 1. Yes? Multiplying alpha 1, alpha 2, alpha 3 should be equal to what we have on the other side, A, B, C. This is what you end up with at the end of the day. So we're going to carry out elementary row operations to see under what condition will a solution exist, okay, for this set of equations. And that means that we should be able to establish now that a solution will exist irrespective of the for every value of A, B, C we can have, there will always be values of corresponding values of alpha 1, alpha 2, alpha 3, such that we will be able to express any one of them in this form. So if we are able to establish that, then we are good to go. We have successfully shown that this actually is span of R. So look at it now. So I can write that, listen very well. I can produce a augmented matrix and carry out elementary row operations on the augmented matrix. This is going to give us 1, minus 1, 0. Augmented means that this constant term I have there, I'm just going to include it on a separate column. And then I have this to be 0, 2, and 1. Then I have this to be 1, 3, and minus 1. So what is the next thing? I have to now reduce this, okay, or express it in the row reduced echelon form, or row reduced form. Right. So I believe everybody can do that at this stage. So I want you to do that yourself. Tell me the results. Don't forget that whatever you are doing will affect A, B, C. Like we did the last example. So work on that and tell me your results. Everybody, work on that and tell me your results. Elements here is already 1, so there's no issue with that. Because it's already 0, you need to clear all every other thing in this column. You need to make them 0. To make this 0, you can just subtract. You can say arrow 3 equal to arrow 1 minus arrow 3, or arrow 3 minus arrow 1. Anyhow, okay, so this is going to be giving us 1, 0, 0, minus 1. This is going to be minus 1, 2, and then 3, minus 1, minus 3, now minus 4. It's going to be 0, it's going to be 1, 2, and then 0 minus minus 1, that's going to be 1. Then I have here A, B, And this one's going to be what? A minus. That's what we have right here. So what's the next thing? Move to the second column, right? Second row. The first non-zero element is 2. It ought to be 1. So to make it 1, we divide by 2. Exactly. We divide it by 2. So we say that R2 is equal to R2 over 2. So this is going to give us 1, 0, 0, minus 1, 1, minus 4, 0, 1 over 2, 1. And we have A, B over 2, A minus. What's the next thing? I need to make this one 0. Abi? This one should become 0 and this one should become 0. To achieve that, I can say R1 equals to R1 plus R2. I told you to clear these things, you have to use this one. You have to use the row of this one as reference. Clear off the others. Clear this off. I can say that R3 equals to. What should I use here? Clear this off. 4 R2. 4 R2 plus R3. 4 R2 plus R3. When you do that, this is going to remain as it is, 1, 0, 0. It's going to be, this is now becoming 0. This is 1, this will become 0. And I have here R1 plus R2. That is 0 plus 1 over 2. That is 1 over 2. I still have here 1 over 2. And 4R2 plus R3. 4R2 is 2. Abi? What times this is 2 plus R3. That is 1 plus that will be 3. Is that clear? Do you understand that? So what's the next thing? We're going to have this thing to be A plus B over 2. A plus B over 2. Then I have for the next one 4R2. 4R2 is going to be 2. I did R1 minus, not R3 minus R1. If we did something different, it's fine. You get that? If we did R3 minus R1, is correct. Okay, so this is going to give us B over 2, and this one will give us what? 4R2. That's 2B plus this. That's 2B plus A minus C. Is that clear? Alright. Then the next thing is to move to the last row. On the last row, the first non-zero element is 3. We want to make it 1, so we divide by 3. Is that clear? To make it 1, we divide it by 3. So I'll say that R3 is equal to R3 over 3. So with that, we will obtain this result. That's going to give us what? 1, 0, 0, 0, 1, 0. Let me order those ones so far you read correctly. And that still remains 1 over 2, 1 over 2. This will now become 1. And then I'm going to have this to be A plus B over 2. This is still B over 2. And this is going to be everything here divided by 3. That will be 2B plus A minus C 1 over 3. That is about that. And I need to clear off these ones. And to do that, I need to use this. Abi? So I will say that R1 should be equal to 2R1 minus R3. R2 should be equal to 2R2 minus R3. Is that clear? Alright. So this is going to give us what? This is going to give us 1. It's not going to alter these ones. 0, 1, 0. This is going to become 0. This is going to become 0. This is now 1. So 2R1 minus R3. That is going to be what? 2 multiplied by this minus this. I can do that separately. I don't need it. I can do rough form separately. 2R1 is going to be 2A plus B. Do you understand that? And can multiply this by 2. 2a plus b minus r3. That's minus 1 over 3 into 2b plus a minus c. Right? So let me give us what? The base, that will be 2 minus 1 over 3. 2 minus 1 over 3 is what? That will be 2 minus 1 over 3. What's that? 5 over 6.
It's 5 over 3.
5 over 3. Okay. Alright. Then we're going to have b minus 2 over 3. So what's 1 minus 2 over 3? 1 over 3. So that will be plus b over 3. I'm going to have the next one. For c, that will just be minus c plus c over 3. That will be 1 over 3 into 5a plus b plus c. Bracket. It's going to be plus 1 over 3 into 5a plus b plus c. The next one, by doing the same thing, 2r, 2 times r2 is b, minus r3. So b minus r3, again I'm going to have b minus 2 over 3, that is 3 over 3. 1 over 3 b plus a minus b minus a plus c. Do you understand that? Do you get that? And find an image, we're not doing anything to this, anything like that. This is going to be 2b plus a plus a minus c over c. That is all we have on this system. That yes. What's the issue? What do you think you're meant to do?
Flying boy.
When you make this become zero,
Focus.
I'll make this become zero. You know that? When you start this class, when you get there, when this is 1, you have to make every other thing in this column become zero. And to do that, you have to use this results. And you have to use arrows to clear off the others. You understand that? But to make this become zero, when you multiply this by 2, it becomes 1. And you subtract this one from it, it becomes zero. You understand that?
And the R1 equals 2 R1
2 times 1 over 2. Oh. Okay, this thing is going to make this one 2.
The other one is 2 R1.
Okay, it's going to make this one 2. Yeah. Thank you.
Yeah, welcome, sir.
So we're not meant to do something like this, right? So we're meant to do something like, look at it, R2 minus R3 over 2. You get it? So be R1 minus R3 over 2. Yes, right? So this is the property. This gives us 1 over 2. You understand what I'm doing? If you know what that was, we have 1 is equal to 0. Half a plus b over 2, that will be what? So we've not done something like that. Okay, so this is going to give us what? I'm going to have R1 minus R3 over 2. So R3 over 2, that is everything we have divided by 6. Alright. So R1 minus that's going to give us A plus B over 2 minus 1 over 6 equals A, sorry, 2B plus A minus C. What will this give us? This is going to be 6A over 6 plus what will this be? 3B average 1 over 6 minus 1 over 6. 2B plus A minus C. 2B equal to So when you pick 6a minus a, that will be 5a. So I'm going to have here 5a over 6. You get that? 3b minus 2b, that will be plus b over 6. Is it clear? And I'm going to have plus 6 over 6. So you're going to equal to 1 over 6 into 5a plus b plus 1 over 6 into 5a plus b plus c. Then for the second part, r1 minus r3 over 2. What would that equals? r1 minus r2, sorry, minus r1 over 2. This is going to be b over 2. C over 2 will be calculated as 3b over 6 minus 1 over 6 into 2b plus a minus c. This is equal to 3b minus 2b, that is b over 6. And now be minus a over 6 plus c over 6. This will be 1 over 6 into b minus a plus c. And 1 over 6 b minus a plus c. This is going to be as it is 1 over 6 into 1 over 3 b plus a minus c. That's that. You can write out the result now. Equal to 1 over 6 into b minus a plus c, and alpha 3 equal to 1 over 3 into b plus a minus c. Please pay attention now, pay attention. So obviously, alpha 1, alpha 2, and alpha 3 will be defined for all values of a, b, and c. Is that clear? That means for any real number, that is for any element of the space R3, there is going to be corresponding values of alpha 1, alpha 2, and alpha 3. Does that make sense to you? You get that? So that means the span of that vector, that set of vectors we were given, okay, is the whole of R3. Why? For every element in R3, there will be corresponding values of alpha 1, alpha 2, alpha 3. Is that very clear? Do you understand this? That means that any vector in R3 can be defined as a linear combination of the vectors we started with, vector 0, 1, 0, 1, minus 1, 2, 3, 0, 1, and minus 1. And so, we can say R3 is the span of that set of vectors that we give. Is that clear? Is this clear? So, say that obviously, since alpha 1, alpha 2, and alpha 3 exist for all values of A, B, C, R3 is indeed equal to the span of S. You get that? The span S all of R3. I mean, every element in R3 can be written as a linear combination of the elements in S. So that is that outside. Describe span S. Describe span S where S equals 1, minus 1, 0, 0, 1, 1, 3, minus 5, minus 2. Define span S where S equal to this. Define span S where S equal to this. Define span S where S equal to this. So you approach the question or this problem a simple way. So you want to find out, listen. because it is a set of three-dimensional vectors, listen now, you can see that S, okay, is a subset of the space R3, obviously. Alright. So we will consider, listen now, we will consider an arbitrary three-dimensional vector A, B, C, okay, such that ABC is a linear combination of these vectors, and try to find out what will be the relationship between A, B, and C. I mean, are there restrictions as to the values of A, B, and C that we can have? And so such restrictions will help us define what the span of this set of vectors is. Is it making sense to you? So I will say, like we did in the previous one, so I will say that let's X, or whatever you want to call it, equal to A, comma B, comma C, be an element of the span S. Okay, let's be an element of span S. If it's an element of span S, that means what? That means you can be written as a linear combination of the elements in span S. Sorry, elements in S. That means that we follow that S is clear vector to be writing about alpha 1 B1 plus alpha 2 B2 plus alpha 3 B2, where B1, B2, B3 are elements of S. Does it make sense to you? I remember the definition of span S. Any vector in span S should be writable as a linear combination of the elements in S. So if this is an element in span S, then I should be able to write it as a linear combination of the elements in the set S. Alright, so it will follow that A, comma B, comma C should be equal to alpha 1 into 1 minus 1 0 plus alpha 2 into 0 1 1 plus alpha 3 into 3 minus 5 minus 3. That clear? Alright, so again we have another set of equations which when you put it in the augmented matrix form, we have 1 minus 1 0 0 1 1 3 minus 5 minus 2, and you're going to have this to be A, B, C. So again, you perform your elementary rule operations and see under which conditions will solution exists for this equation. That is, are there going to be restrictions on the values of A, B, C, or the values of A, B, C can be just anything? And if they can be just anything, that means the span is R3. It can be any element from R3. Do you understand what I just said? Any vector from R3. And if there are restrictions, that means again it will be elements from R3, but not all elements from R3. It will be some elements in that specific property from R3. Right. So go ahead and reduce to the echelon form and see what relationships need to exist between A, B, C for a solution to exist for this equation. Okay, so 1 0 0 0 1 0 0 1
3 minus 2.
0. Yeah. Alright. A plus B. C minus A plus B. A plus B in bracket. A plus B minus C. Yeah. C minus A minus B. Yeah. So under what condition will the solution exist? Yeah, this thing has to be equal to 0 for solution to exist. Do you understand that? If you multiply this out, you know the meaning of this augmented matrix is 1 0 3 0 1 minus 2 0 0 0 multiplying alpha 1 alpha 2 alpha 3 must be equal to A plus B C minus A minus B. Is that clear? So that means when you multiply this out, this is going to give you alpha 1 plus 3 alpha 3 should be equal to A, Abi. And the next one, alpha 2 minus alpha 3 should be equal to A plus B. And the last one is going to be 0. 0 must be equal to C minus A minus B. Is that clear? So we have freedom, since we have freedom concerning values of alpha 1, alpha 2, and alpha 3. what must first hold for anything at all, or before we can consider anything, is that this thing must be equal. If these two are not equal, definitely there is no solution. Is it making sense to you? Alright. That means that we can express an element R3 in this form only when this condition is satisfied. That means that this C must be equal to A plus B. Is it making sense to you at all? You understand what I just said now? Alright. So that means that, listen, the span of S here is not all of R3. Why? Because it is not for all of R3 that you will have A plus B to be equal to C. Does it make sense to you at all? You understand this? So it cannot be all of R3. So it will only be those elements or those vectors in R3 for which C is equal to A plus B. Is it making sense to you? If C is not equal to A plus B, that condition will not be satisfied, and that element will not be expressible as a linear combination of the vectors in S, which means that particular vector will not be a member of span S. So the members of span S are the elements or the vectors in R3 for which C is equal to A plus B. Does that make sense to you at all? Does it make sense to you? So I can write that span S is equal to, please pay attention, the set containing vectors X is such that you can write it this way, such that, or you can put a line like this, X such that X is equal to A, comma B, comma C, and C is equal to A plus B. You can write it this way, A, B, C. Let us write this as element of R3 such that C is equal to A plus B. That's what that will be the span of S. It has specific elements it can carry. There must be such element for which C is equal to A plus B. So if C is not equal to A plus B, it is not a member of span S. Does it make sense? So let's move on. Theorem. You can write it down. Theorem. Let V be a vector space. Let V, that's big V, capital letter V. Let V be a vector space over the field F. Let V be a vector space over the field F. Full stop. The intersection of any collection of subspaces, the intersection of any collection of subspaces of V. The intersection of any collection of subspaces of V is a subspace of V. Is a subspace of V. Is a subspace of V. Think about that. Does it make sense? Alright. Think about it. Does it make sense? If you think this makes sense, let me see your hand and try tell me what. Explain to us why you think it makes sense. Oh yeah. You didn't talk now. Yeah. What did you say? Okay, so look at it. Let's use sets. Intersection, of any collection, of subsets of a set. It will also be a subset of that set. Do you understand what I just said? Do you understand that? Right. So if you have subsets, like you have something like this, please pay attention to this. You have something like, let's say a set A, B, C. Alright. Set. You have subsets intersection, not union. Intersection. No intersection.
No sense.
Empty set. You can write B or just write something like this without the do you understand that? So this intersection is also a subset of S. Do you understand that? The empty set is a subset of S. In particular, you know that in the case of subspaces, we have said for something to be for V to be a subspace of W, it must have at least a 0 element. It cannot be an empty set. That means that every subspace of W, for instance, has the 0 element. So the intersection cannot be empty also. Is that clear? And also, even if the intersection contains only the 0 element, it is still going to be a subspace of W. Does it make sense to you? Alright, that's the meaning of that. It's just English. Alright, so let's move on. Definition. Definition. Let S be a set of vectors in a vector space V. Let S be a set of vectors in a vector space V. Let S be a set of vectors in a vector space V. Full stop. The subspace spanned by S. The subspace spanned by S. The subspace spanned by S is defined to be the intersection W. The subspace spanned by S is defined to be the intersection W of all subspaces of V. It's defined to be the intersection W of all subspaces of V which contain S. Defined to be the intersection W of all subspaces of V which contain S. Which contain S. Full stop. When S is a finite set of vectors, when S is a finite set of vectors, finite set of vectors, comma, S equal to x1, x2, x3, and so on and so forth, up to xn. When S is a finite set of vectors, that means that's finite element. I believe you know finite set and infinite sets from part 1. Okay? So the finite set of vectors. Okay, you're in web or whatever. You should have done finite set.
You know did it, not so about.
They don't teach us.
You know did it. On this one.
He came here for Chinese. That means it will be better if you fail any everyone is the go one.
Wow. Just a big guy now. Just a big guy.
I'm serious. I'm serious. The truth is that everything is vanity. You want to graduate. You want to marry. You want to buy a house.
Vanity.
You want to get good job. Everything is vanity.
You want to get anything too. Man, you know the teachers of free now. Who never pay every class. Vanity.
What will you do to vanity?
Who never pay me?
Yes, you must take everything slightly. Do you understand? Don't kill yourself because of the certificate.
That first question I'm
my certificate is vanity. I have discarded it. I didn't know then.
No, you don't get out.
This is never said.
When S is a finite set of vectors, we shall call W the subspace spanned by the vectors x1, x2, x3, blah 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 up to xn. We shall call W the subspace spanned by the vectors x1, x2, x3, blah 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 up to xn. Who can explain that statement to us? Read it. Think about it. Explain it. Oh yeah. Think about it. You don't understand that statement?
Yes.
Is it English that is the problem?
Yes.
English is the problem.
You
You can ask to take SCR. So you can take SCR. Don't go to your bad advisor. We have to remove it for that set up.
I'm not going to get that
Let's go to workbook to you now. Alright, so they said, listen. If S is a set of vectors in vector space V. So in the last class, please pay attention. We said that if S, let's pay attention, is a subset of V, where V is some vector space. Please pay attention to this. And then we said that span S is going to be a subspace of V. Can you remember that? Which we actually proved in the last class. Alright, so that's the sense. Listen now. I'm trying to say something similar here. That if S is a subset of V, is a subset of the vector space V, then we can have, if W is intersection, please pay attention. W is going to be an intersection of all vectors, okay, that contains the elements in the set S. You understand what I just said now? That is, all subspaces, every vector subspace you can think of, every subspace of V that you can think of, that contain the vectors in this, okay? That is, their intersection is going to be the same thing as the span of S. What do we mean by that? Okay, it means that, please pay attention to this statement. It means that for all elements in that particular intersection, for all elements in this W, okay, all elements in this W, say, let's say this one contains element X, it is such that I can write X as linear combination of those elements that are in X. Alpha 1 x1 plus alpha 2 x2 plus and so on and so forth plus alpha n xn. So where x1, x2 and x3 and so on and so forth are elements of the set X. Is it making sense to you at all? You understand what I just said? So it will help us as we proceed in this course. We're going to talk about intersection of two or more sets later. We're going to see why and how we define intersection of two or more sets. So W is pay attention. The subspace spanned by S. Okay? The subspace spanned by S. Don't forget you have defined that earlier. The subspace spanned by S, which we said span S. Span S is going to be the subspace which contains this same element. Right? This whole element will be defined this way. Okay? And we have said it's going to be a subspace of the vector space V, which we proved in the last class. And this statement is now telling us that, let's pay attention to this. It's defined to be the intersection W of all subspaces of V which contain S. contain S. Don't forget that S is a set of vectors. Contain S means that it contains all the elements in S. So any subspace that you can think of that contains all the elements in S, okay, their intersection is going to be the same thing as span S. That's the meaning of this. The intersection is going to be the span S. That means, please pay attention. If I have a vector space, let's say I have a vector space. We're going to see an example now. Let's say I have a vector space. The vector space we just defined now. We have it to be X such that X equals to A, comma B, comma C. Please pay attention to this. And where because this is element of R3, where C was equal to A plus B. Is it making sense to you? Do you understand what I'm saying at all? Alright. So we will let's say we have another element, let's say this is W1, and we have another subspace, let's say W2 to be equal to subspace of the same R3. Let's say this one is equal to X is such that X is equal to A, comma B, comma C, element of R3, such that in this case, let's say A is equal to 2B. So let's say this is what actually relates them, and C can take on any value. Right, so we may be interested in getting the intersection of these two. Let's say we are interested in getting the subspace, which is the intersection of W1 and W2. Is it making sense here? We are saying that it's going to be the span. Please pay attention. It's going to be the span of S. That means that we're going to find out the vectors that are common to both of them. If you can write this one in this form, please pay attention. You can write this as a linear combination of some vectors. Let's say alpha 1, 1 into some vector v1 plus alpha 1, 2 into some vector v2 plus alpha 1, 3 into some vector v3. And I can also write the elements in this by our analysis or expand that one. We're going to see an example soon. And I can write this one also as alpha 1, 1. Let's say v1 plus alpha 1, 2. Let's say v2, right, in this case, plus alpha, what is this? It should be 2, 1, 2, 2, and then 2, 3, right? Into some other vector. Let's say this is V star. So at the end of the day, what we'll be interested in is what is common to both of them. What is that particular element that is common to both of them. When I have that particular element that is common to both of them, I will define their intersection. This intersection will now be span of whatever is common to both of them, which I can call, let's say, V1 and V2. So I will say span of V1 and V2 because usually it should be of the three elements. You get what I'm doing here? You understand what I'm doing? That's the meaning of this statement. It looks abstract. Now let's take some examples to understand this. Right, Steve? Pay attention. Another property, write this down.
Property.
Yeah, theorem or property. The subspace spanned by a non-empty subset S. The subspace spanned by a non-empty subset S of a vector space V. The subspace spanned by a non-empty subset S of a vector space V is the set of all linear combinations. The set of all linear combinations of vectors in S. The set of all linear combinations of vectors in S. Okay, we've talked about this before. Also proven this. So just repeated here for emphasis here. Example. We're going to take an example. Let W be the set of all. Let W, that's capital letter W. Let W be the set of all let W be the set of all x1, x2, x3, x4, x5 elements of R5 which satisfy, let W be the set of all x1, x2, x3, blah blah blah, element of x5 and r5 rather, which satisfy the relation 2x1 minus x2 plus 4 over 3 x3 minus x4 equals 0. x1 plus 2 over 3 x3 minus x5 equals to 2. And 9x1 minus 3x2 plus 6x3 minus 3x4 minus 3x5 are 2. Next, we'll be the set of all x1, x2, x3 elements of R5, okay, which satisfy 2x1 minus this blah 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 and this and this. And find a set. So find a set. Find a finite set of vectors. Find a finite set of vectors. Find a finite set of vectors. Find a finite set of vectors which spans W. Which spans W. Find a finite set of vectors which spans W. Which spans So listen now, listen. So how is this, please pay attention. How is this different from the problem we solved earlier? The problem we solved earlier, we were given the vectors, and we wanted to get the span. Please pay attention, We were given a set of vectors. Can you remember the set of vectors we dealt with? Maybe 1, 0, minus 1, blah, blah, blah. We're given a set of vectors. I wanted to find the span of that set. In this case, we were given the vector itself. Do you get what I just said now? We're given the vector space, so to speak. We want to find out which set of vectors actually span this vector space. You understand what I'm saying? Just like the reverse of what we did earlier. Do you get what I just said now? So, if that is the case, that means we are interested in getting, please listen now, we are interested in being able to write these elements, okay, any element in this set, as a linear combination of some set of vectors. We don't know what those sets of vectors are. We want to find out what they are. Is it making sense to you? Right? Provided that these elements are the elements here, or the coordinates of this vector are given by this relationship. So again, we're going to follow the same approach, but we are going to have different end results and interpretation. So in this case also, we will solve this equation simultaneously. You know that we have 5 unknowns and we have just 3 homogeneous equations. You get that? Okay, so again, we're going to use our elementary rule operations to establish whether or not there will be a solution to this equation and what the solutions will be. Do you understand this? Alright. So when we put this together in matrix form, please pay attention to this. In matrix form, you know, I can write this out and say this is 2x1 minus x2 plus 4 over 3 x3 minus x4 plus 0x5 equals 0. Is that clear? And the second one, I'm going to write this as x1 plus 0x2 plus 4 over 3 x3 minus 0 over 0x4 minus x5 equals 0. Does it make sense? You understand this? Right, the next one is 9x1 minus 3x2 plus 6x3 minus 3x4 minus 3x5 equals 0. Does that make sense? Yeah, so in matrix form. So you can write an augmented matrix here, but it is useless because the 0, 0, 0s don't have any effect at the end of the day. They are just going to remain 0 all through. Is it making sense? You can just pick the coefficient matrix and work on it. If you write out the augmented matrix, it's fine, but it's going to be the the part containing the constant element are going to be 0 or true, irrespective of the operation you are carrying out. Is it making sense to you? Alright, so this is going to give us a matrix form. I'm going to have this to be 2 minus 1, 4 over 3, minus 1, 0. We're going to have 1, 0, 2 over 3, 0, minus 1. And this is going to be 9, minus 3, 6, minus 3, minus 3. So in augmented matrix form, if you like, it's going to carry 0, 0, 0. So this is that way. Then you carry out elementary row operations to have it in row reduced form. Is that clear? Have it in row reduced form. So what will be diagonal now? What is diagonal? That is why the definition never mentioned diagonal. So the definition only says the first non-zero element in each non-zero row should be 1, Abi. And then every other element in the column of that particular non-zero element must be 0. That's all. Do you understand that? That has nothing to do with whether it's a square matrix or not. Is it clear? Alright, so what's the first non-zero element here? 2. We're going to make it 1. How do we do that? Divide all 2 by 2. That means we're going to say that R1 is equal to R1 over 2. When you do that, this will have this thing. 1 minus 1 over 2. 4 over 6. Minus 1 over 2. 0 and 0. Then this one is going to be 1, 0. 2 over 3. 0. Minus 1, 0. So 9 minus 3, 6 minus 3, minus 3, 0. Is it clear? What's the next thing? I'm going to clear off every other element in this column using this as my reference. Is it clear? So I'm going to say that R2 is equal to R2 minus R1. Is that clear? R3 is equal to R3 minus 9R1. Does it make sense to you? You won't be multiplying the particular row by a number, just like we saw the other time. My upper distribution. So this is going to give us what now? I'm not doing anything to R1. This is going to be 2 minus 1 over 2, 4 over 6 minus 1 over 2, 0, 2 will be 0. And then I have this to be R2 is equal to R1, R2 minus R1. This is going to be 0. This minus this, that's going to be 1 over 2. This minus this. 2 over 3 and 4 over 6, they are the same, right? So this minus this is going to be 0. And then this minus this, basically I can also put 2 over 3. Avoid confusion. This is going to give us what? 0 minus this is again going to be 1 over 2. And then minus 1 minus 0, that's going to be minus 1. This is going to be 0. So I have the third row. R3 minus 9R1 is going to be 0. 9 times this is going to be minus 9 over 2. That will be plus 9 over 2. Minus 3 plus 9 over 2. What will that give us? That is 3 over 2. Please confirm that. Correct? Is that correct? Yes. Alright, so this is going to give us R3 minus 9 times R1. 9 times this is going to be 6. Alright, 6 minus 2 over 6 is 0. Right? Yeah, it's 2 over 6. 4 over 6 is 2 over 2. Don't stress us. This is going to be minus 3 minus 9 over 2. Basically, doing the same thing as this. And this one is going to be what? Minus 3, minus 0, minus 3, and 0. Back there. What's the next thing now? I have the first element in the second row is 1 over 2, right? To make it 1, what do you think I should do? Divide by 1 over 2 or multiply by 2. Alright, so this is going to be R2 1 minus 1 over 2. 2 over 6 minus 1 over 2. 0. So 0, 1, 0, minus the element in its root. So we say that this is going to be equal to R1 equal to R1 plus R2 over 2, right? Do you understand that? I want to make this 0. Sorry, 3 over 2 R2. Do you understand that? When I multiply this by 3 over 2, it will become 3 over 2. Abi? Subtract this from it. Now will become 0. So we can make one that. So what will this give us now? So this is going to give us 1 minus 1 over 2. 1, 0, Abi. Next one is going to be what? So remain 2 over 3. On to the next one, that will become 0. And the last one, R1 plus R2 over 2. R2 over 2 is minus 1. 0 plus minus 1, that's a minus 1. 0. So the last second one, we're not doing anything to it. 0, 1, 0, 1, minus 2, 0. And last one, R3 minus 6 will be 0. And this is going to become 0. R3 minus 3 over 2. So this is going to be 0. This one, R3 minus 3 over 2 is not going to be 0. What of this? That's going to give us 0. Everything here is 0. So we're good to go, right? So we have it in low reduced form, right? Is it clear? We now have it in low reduced form. Wow. What's the interpretation of this? Of course, it will have a solution. Like 0 is equal to 0. Yeah, so that's not an issue. So when you expand this, what are you going to get? You're going to get 1 multiplied by x1. I mean, so I'm going to have this to be x1 plus 2 over 3 x2. Sorry, x3. Minus x5 equals to, and from the second line, or second row, we're going to have x2 plus x4 minus x5 equals to 0. These are the two relationships that must exist between them. Right, so how do we make use of this relationship to get what we need to get? Please pay attention. So we're going to set up parameters here. So this means that, listen very well, you can see you have x1, you have x2, x3, x4, x5 right here. Please listen very well. You are free to listen, please. You have only 2 equations. Okay? That means that you are actually free. You have only 2 equations. Normally, 2 equations should give you 2 unknowns. Have you now? So it means that you are now at liberty to pick the values of the remaining 3. You understand what I just said now? Right? So the remaining 3 are what we call free variables. You can assign any values to them, and for any value you assign to them, there will be corresponding values of x1, x2, or the other 2 variables assigned to them. So what we can do here is, please pay attention to this. So we can say that let's x5, this is my choice, equal to alpha, or say, yeah, alpha, and x4 equals to beta, I'll say x3, x4, and x5 will be equal to gamma. Please pay attention. If that is the case, then I can write that, please pay attention, therefore, x1 will be equal to, so I can substitute all of this, that will be 2 over 3, x3 alpha minus this minus gamma. When I move this out of here, minus will become plus gamma. Is it clear? Then I can write that x, what's this one? X2, the next one, is going to be equal to, when I move this outside, minus x, that's minus beta, plus 2 gamma. So I can have this expression. That means that we are free to choose, or at liberty to choose the values of x3, x4, and x5, and when that is closing, their value will determine those of x1 and x2. Is it making sense to you? Yes. So, based on this, we can write out our results. Please pay attention to this. That means, therefore, our x1, please pay attention to this. x2, x3, x4, x5 can be written as, listen very well, I'll put this here. What is x1? Minus 2 over 3 alpha, okay, plus gamma. And x2 is what? Minus beta plus 2 gamma. x3 is what? x3 is alpha, x4 is beta, x5 is gamma. So that means if we separate them, we write them all out separately in terms of alpha, beta, and gamma. We will obtain this as well. Please pay attention to this. So the parameters we have here are alpha, beta, and gamma. So based on this, I can say that x1, x2, x3, x4, x5 is going to be equal to, please pay attention to this. Alpha is the first parameter I have, alpha into, so I'll take out alpha from here and see and write other things in terms of alpha. So this is the same as alpha into minus 2 over 3. Okay? What other thing? Where do I have alpha again? I have alpha in this first one. Did I write x2? Minus beta, yeah. So x2 doesn't have alpha, that will be 0, you understand what I'm doing? You understand what I'm doing? So I'm factorizing now, just move out alpha from here. Okay? I want to be able to separate out the terms in terms of alpha, beta, and gamma. Is it clear? Right. So the coefficients of alpha minus 2 over 3 in the first term, the first coordinate, coefficient of alpha is minus 2 over 3. The second coordinate, the coefficient of alpha is 0. The third coordinate, the coefficient of alpha is 1. And this one, 0, 0. Is it clear? So this is 1, then this is 0, this is 0. Does that make sense? Do you understand that? Do you understand what I'm doing? Okay. Just follow it if you don't understand this. It's going to be plus beta. I'll pick beta next. I'll write out the coefficients of beta. The first one, the national coefficients, that is 0, beta in the second one, minus 1, the next one, 0, 1, 0. And I add, finally, the last parameter is gamma. So gamma in the first one is what? 1, the second one, 2, the third one, 0, fourth one, 0, the last one, 1. Is it making sense to you? Does that make sense? So what have we done now? We have successfully expressed the vector or the element of the vector space as a linear combination of this vector, and this vector. Does it make sense to you? Do you understand this idea? That means the elements, listen now, listen. This means that alpha, beta, and gamma, of course, can be any value. Whatever value of alpha, beta, and gamma you get, we're going to get corresponding values for x1, x2, x3, x4. You understand what I just said now? And x5. So that means the elements here that satisfy the equation we were given can be written as a linear combination of these vectors. Is it making sense to you? Is it clear? Is it clear? So that means that the vector space we started with is a span of the set containing this vector, and this vector. Does it make sense to you? What is the span of a set of vectors? The span of a set of vectors is that vector space that contains elements that can be written as linear combination of the vectors in that set. Is it making sense to you? Right. So that means what I have here, please pay attention to this now. So that means that the set, what do they call the set in the question? This vector space. W, that means that W is equal to the span of this vector, okay, this set of vectors, minus 2 over 3, 0, 1, 0, 0, okay, 0, minus 1, 0, 1, 1, 2, Is it making sense to you at all? Do you understand this? If W is a span of this set, that means every element in W can be written as a linear combination of the elements in this set. Is that true? Yes, that's what we just established. Is it making sense to you? Do you understand that? Right, so that is that. So that is the set that span W. Where do we start from? Yeah, this is the solution of this equation. Whenever you have an equation like this, that you have some free variables. Free variable means that they can have or they can be given any value, and any value you give them, you also have corresponding values for the others and the other variables. Something you also solution of linear equations. Yeah, whenever you reduce, so you have your equation in row reduced form, like this. So you have expressed it in row reduced form. Count how many unknowns do you have here. If you have 3 unknowns, for instance, and you have 2 equations at the end of the day, that means you have 1 free variable. Is it clear? You know, the number of unknowns should be equal to the number of equations. But when the number of unknowns has exceeded the number of equations, then the difference is the number of free variables that you have. You understand what I just said? So we are going to assign arbitrary values to those free variables. Is it making sense to you at all? That means what I have done now, I could have as well said x1 is equal to alpha, x is equal to beta, and x2 is equal to gamma. It will be changing. You still get so if you have 5 equations, or if you have 5 unknowns and 2 equations, that means there will be 3 free variables, which is what you have here. If you have 4 unknowns and 2 equations, that means there will be 2 free variables. Abi? And those free variables will then be used to obtain the others. Is it clear? If you have 3 unknowns, 2 equations, that means you are going to have 1 free variable. That's the way it works. If you set x3 to any value, let's say you set x3 to 1, x4 to 1, x5 to 1, we will still have an equation that will satisfy this. We still have a solution that will satisfy our values of x1 and x2 corresponding to those values that will satisfy this equation. So we have an infinite set of solutions. We are not done. We are not done. Alright, so the question says you should find LWBD said find a finite set of vectors which spans W. So we have found the finite set of vectors. So this is the set of vectors that span W. Is it clear? Alright, so that's that about that. So let me give you an assignment to move on from here in the next class.
I did, it motivates me.
Who's motivating you?
You just stand up. I'm full run.
Assignment, right. Is the vector is the vector is the vector 3 minus 1 0 minus 1 is the vector 3 minus 1 0 minus 1 in the subspace of R4, the subspace of R4, in the subspace of R4, spanned by the vectors, is the vector this, in the subspace of R4, spanned by the vectors 2, minus 1, 3, minus 1, 1, 1, minus 3, and 1, 1, 9, minus 5 is the vector this in the subspace of R4 spanned by the vectors this, this, and that. That's the question. 2 minus 1, 3, 2, minus 1, 1, 1, minus 3, 1, 1, 9, minus 5. So So we're done. So what do you think you're going to do here? What do you think we are going to do here? The question is please pay attention, pay attention. Please pay attention. Alright. The question is equivalent to asking you if this can be written as a linear combination of that. Is that clear? Do you understand that? So I'll see you when I see you.